This address is being presented by our 2013 Olney Medal recipient, Dr. Charles Yang, professor in the Department of Textiles, Merchandising, and Interiors at the University of Georgia. Dr. Yang received a Bachelor of Science degree in chemistry from Beijing University in 1969, a master's in polymer chemistry from Nanjing University in 1981, and a PhD in analytical chemistry from Kansas State University in 1987. From 1987 to 1990, he was an assistant professor in the Department of Chemistry at Marshall University. In 1999, he joined the Department of Textiles, Merchandising, and Interiors at the University of Georgia, and in 1995 was promoted to professor. Dr. Yang began his research in textile chemistry as a graduate student while at Kansas State. He continued his research on chemical and instrumental analysis of fibers and fabrics while at Marshall University. After joining the faculty at the University of Georgia, Dr. Yang extended his research to textile functional finishings and established himself as a world-renowned scholar in the fields of cotton durable press and flame retardant finishing. His contributions are in three specific areas: flame retardant finishing of cotton and cotton blends, non-formaldehyde durable press finishing of cotton using multifunctional carboxylic acids, and chemical and instrumental analysis of chemically modified textile fibers. The title of Dr. Yang's Olney Medal address is Cross-Linking, a Route to Improve Cotton Performance. Dr. Yang.
Thank you, Professor Hauser, and I'm very grateful to AATCC and Dr. Keith Beck and many other members of AATCC give me the honor and the opportunity to give this speech today. And compare with most of the people here, my experience is a little bit different because I'm from a different country. And also I become a textile chemist is kind of by accident. And I went to the university quite early in 1963. I went to the Peking University, which actually is the best university in China. But then in 1960, for us, it's in October 1965, the Cultural Revolution actually started. So I lost 12 years of my prime time. And from 1966 to 1976, which is where chaotic political turmoil we call the Cultural Revolution. And for 12 years, actually, I did not have a single day can go to classroom or go to lab or read a textbook. Then in 1978, the China political orientation changed. And I went back to Nanjing University for my master's degree. And even though, there's a 12 years gap. And then after 3 years, in 1981, I finished my master's degree in polymer chemistry. And at that time, China did not have PhD program. China PhD program started 1983. So I applied to a few universities in the United States for PhD. And that time we did not have much knowledge about the higher education system in the United States, even though I did have some information. So I get an offer from Kansas State University chemistry department. So I accept the offer immediately. And then when I come to Kansas State, I find out I could not do anything polymer chemistry related because they only have 4 branches: inorganic, organic, analytical, and physical chemistry. So finally, I find a major advisor, late Dr. Bill Faithley, who was 22 years for the editor of Applied Spectroscopy. And he agreed to accept me work on polymer-related project, assuming I could develop my own project. So the only way for me to develop project is work for the textile department in Kansas State. So I find a professor, and then through that professor, also I had some relationship with the USDA Southern Regional Service in New Orleans. So this is why my PhD dissertation was used infrared acoustics, FTIR acoustic spectroscopy to study chemical modified fibers and fabrics. So this is how I started. And after 3 years at the Marshall University, I coming back, actually change my whole area from chemistry to textile by joining the textile department in University of Georgia. So I started. So today my topic is cross-linking, a route to improve performance. I would give a basic background, and then I would focus on my today's presentation on the non-formaldehyde press finishing of cotton. And also in the last 10 years, I actually extended my research in the durable press finishing area to a fairly tightened finishing area. These two areas are very closely related. And but I will only have a few slides because I only have 30 minutes time, so for the 35 minutes. So, okay, let's see. Today I'm discussing the chemical modification of cotton. And cotton is the hydroxyl functional bipolymer. Okay. It has the it has the OH groups, particularly C6OH is quite reactive. So the chemical modification is based on the reaction with the hydroxyl groups. And the durable product finishing is a major area in textile functional finishing, which is to improve the wrinkle resistance or wrinkle release properties of cotton. And the reason for wrinkle formation is because of the hydrogen bonding between the hydroxyl group cellulose. And the method for improve the wrinkle resistance is by cross-linking the cellulose when the fabric is pressed or the garment is pressed. So after the cross-linking, it will achieve the smooth appearance, wrinkle resistant, and the wrinkle release. As the technology is started in 50s to 60s, they use formaldehyde or phenolformaldehyde, urea formaldehyde, and melamine formaldehyde. But that was not very widely used. Then in 1970s, started using DMDHU, and then in the 1980s, developed so-called low formaldehyde or ultra low formaldehyde DMDHU. But the DMDHU has a problem, which is formaldehyde. And this is a DMDHU which is in equilibrium with the formaldehyde. If you increase the temperature, if the finish is applied on the cotton fabric, then you do the drying or pressing or curling at extremely high temperature, the DMDHU will decompose to release the formaldehyde vapor. So this is cause we call acute exposure to the textile workers. And there was a study on the health effect in the New York City area, and for the formaldehyde. But that's not all. Also, another is a chronic exposure for the consumers, because when the DMDH form cross-link, it hydrolyzes, not only during the laundering, but also during the storage by the high content of moisture on cotton fabric. So once this linkage hydrolyzes, so this is the methyl group, then it will release formaldehyde. Means if you put a garment or put the garments and actually it's more than just garments and the whole finishing material that use the DMDHU. And then the continuously the formaldehyde is released. So this is present a risk for consumer because human use garments from the beginning of your life to the end of your life. So the whole life, this is really, the textile is a very intimate part of the life because all the time, day or night. So this exposure, low intensity but very long time exposure, the health risk is not fully evaluated, assessed. And the formaldehyde risk in the 1970s, they had laboratory data link the gene mutation with formaldehyde. Then 1987, EPA has a report, and the formaldehyde becomes suspected carcinogen, which is probable carcinogen. And in 2004, the WHO, World Health Organization, there is called International Agency for Research and Cancer. They publish article. Actually, that article is very interesting. This article is in this very famous journal, Linked Oncology. Only one page, but it didn't summarize. They upgrade the health risk for formaldehyde to group 1. Group 1 is the highest risk. They are called carcinogenic to human. So this is this report is 3 chemicals. Okay, the formaldehyde is only chemical in that highest rank. So the traditional method to solve that problem or to manage that problem is use diethylene glycol, okay, to incorporate with DMDHU, which is actually can perform. So that's terminate that formaldehyde, group, and by doing this, the molecular weight actually increased by almost 100%. And but this the modified low formaldehyde version of there's different versions, and formaldehyde level is decreased by 50% or even more, but it's still significant. At the same time, the chemical becomes less reactive. The reactivity is reduced, and the quantity is increased. You need to double the quantity, but the price also increases. So you have high quantity, and at the same time also at a high price. The total cost is also significantly increased. But the problem is this, because the ethylated, this is modified DMDHU, still based on formaldehyde as the reagent for class inhibitor. This is still formaldehyde based. Also, the reduction is only for the free formaldehyde, because the testing method is free formaldehyde, but not the total formaldehyde. The total formaldehyde is no decrease or even increase, because sometimes you use more. And those formaldehyde will be released at the same time of when the garment is being used. So this is a problem. And in the market now, the only non-formaldehyde is called DMDHI, which is glycolated derivative of urea, and which actually is, I think is being used in the Chinese companies. But it is a relatively lower reactivity. They use much higher quantity. They have the odor problem or yellowing problem. I believe those problems, when after their use, is managed to minimize, but still is a problem, and also a high cost and the original catalyst with the patent is not considered to be environmental friendly. So this is, I call it a limited success. And then in 1988, this is just before I moved to Marshall University, Dr. Clark Welch, a scientist in organic chemist in USDA Southern Regional Service, he published his paper in TRJ using the BTCA. But the BTCA was published in 1960s. But Dr. Clark Welch's contribution is he found the sodium hypophosphate as the most effective catalyst. So this is where I started. I met him in 1989 in New Orleans with the Pittsburgh conference. So so this is he inspired me. He also gave me a big encouragement. So I start the research in this area. And my research is first, as a chemist, we always want first to know what happened, not what it can do. This is so I start with the chemical reaction mechanism, and then when we start to understand how it reacts, then I try to develop more practical derivative process finish systems. I have three systems I discussed. And then also there's another issue associated with the derivative process finish, which is the strength and abrasion resistance of the finished fabric. So I have studies in these three areas. And the reaction mechanism was mentioned in Dr. Clark's Welch's paper, 1988 paper. It's possible from anhydride intermediate, but there was no evidence. Then in 1989, AATCC conference, which is in Philadelphia, of course that time was a much big conference. And also there's a paper indicated that believe there is the paper was given by another researcher from USDA to mention that reaction mechanism, but that was only a speculation. And so my first work when I moved to UGA is I think I can do a work relatively simple to see if it is the case. So I used two isomers of it's a bifunctional unsaturated carbonic acid, and with malic acid, which is cis isomer, when another is fumaric acid, is trans isomer. So if I put them to the cotton fabric under identical conditions, which we can specify and which can cross-link. That's what this was done at Marshall. So I did not have a legal recovery test, but we did have a FT IR spectrometer, which was my PhD research area. So I used this and I proved that the only malic acid is possible to esterifiy cotton, and also the esterification increase as a temperature increase or as a catalyst with catalyst use. So I published the first paper in TRNT. That was my first paper in the area of textile chemistry. And then a few years, I examined 16 polycarbonic acid with relatively small molecules. This is bifunctional. Then we have three carboxyl group and soft and saturated and unsaturated and aromatic and the different functional, the BTCA, and then we have a polymeric, even polymeric. And so I identify all the formation of the anhydride which is on cotton. Also, this is the ester carbonyl bond. This is relatively tell you how much ester, and this is the concentration. Some of them I have used ethanol to improve the solubility. And here I should just show you example. So this is I feel pretty excited that I won, because as infrared spectroscopy, I find that carbonyl is a very good way to study because it has a high dipole moment. The intensity of infrared band is proportional to the change in dipole moment during the vibration mode. You know, for the this is anhydrate, cyclic anhydrate. You know, you have the stretching, or you have called symmetric stretching. You have asymmetric. Asymmetric is like this, and this stretching actually has two unique band widths. The difference is also is set. This is a unique characteristic, not only on the band frequency, also different between these two bands. And so this is cotton with BDCA. This is curve, the curve at the 170 degrees for 2 minutes. Then we see a two band. Then we can do a spectral subtraction because when we have FTIR, the frequency is very precise. We could frequency precision advantage. So we do spectral subtraction with very high accuracy. And so we will see this is 1848, which is symmetric stretching, 1779, which is asymmetric stretching. That's the ester. We use the base, we use the sodium hydroxide to convert the free acid. Then we will see that this is carboxylic ion, which is the basic form of acid, which is ester. And then I'll give you I published a number of papers in this area, but I can give you one example. Is we'll see this is three functional, both are three functional, but it has CH2 between. And then you can see this is just the acid form 100. And this is at the 140 or 120 degree. Okay? We'll see that this is without formation of other, but you see the free carboxyl groups actually is not entirely free. We see the 1736 and 1703. 1703 represent the hydrogen bonded, either intermolecular or intramolecular. But this is free. These are similar. This is for 1,2,3 acid. This is 1,2,4 acid. And you see these two forms. But once you have very high temperature to form anhydrate, only the hydrogen bonded stay, and those truly free carboxyl group form anhydrate. Now this is very similar. Also, the anhydrate is very similar, but you can see the ester carbonyl binding intensity is different because when this is a 1 to 4 is much lower than 1 to 3 at the same temperature. And this is indicate that the 1 to 3 is for more ester. Why? Then we can expand because 1 to 3 can form one anhydrate and esterification and second anhydrate then form a cross-link. But for the 1 to 4, once you form the first one, and second one, you have to form 6-membered anhydrate. Now, I have a more research. I 6-membered, but 6-membered is far less reactive, require a much higher temperature. But now, can we find experimental evidence for these two anhydrates? This is the first one, this is the second one, to prove that they are truly two anhydrate form, which I achieved. Okay, here this is 180 degree. We cure for 2 minutes. Then we do a spectral subtraction, 1852, 1783, which is the first anhydrate mostly. And because this is anhydrate formed, which is not esterified, But the second one is we use much higher concentration. We use 8% concentration, then we use 15 150 degree, 2 minutes, then we wash. So this is, we believe it only forms one single ester linkage. Then we use the acid to convert all the free acid group to acidic form, and then we clear at 180 degrees for 2 minutes. Then we can see that this is two different mechanisms. This is 1853, 1774. Okay, the difference is 9. It's 9 wave number. Okay, it's 9 wave number, and but it is much lower. It is 9 wave numbers lower, 1953 to 1952. For this, as a spectroscopy, the 9 wave number cannot be, absolutely cannot be an artifact. This is two different hydrates. So let me summarize my findings. The five-membered cyclic anhydride as reactive intermediate formed and cut treated with polycarbic acid under cooling conditions. And a polycarbic acid must have 3 or more carboxyl groups bound to the adjacent carbons in backbone. If you have to have the adjacent, then you form 5-membered. If you have CH2 between, then it becomes 6-membered. And 6-membered cyclic anhydride intermediate require higher temperature to form, and also is least reactive to esterified carbon. So such polycarbic acid are effective cross-linkers, but it is far less effective than the 5-membered. And for those carboxylic acid which are capable of forming both 5-membered or 6-membered, from the structure, it can form both in the same molecule. It only forms 5-membered anhydride intermediate. And also the reactivity of polycarboxylic acid for estifying cross-linking carbon is affected by their molecular size, by molecular weight. And the smaller size, like BTC, is more effective than larger ones, the large size. This is which we use to develop new cross-linking systems. And also we find that the carboxylic acid in crystalline state start to form 5-membered cyclic anhydride at their melting point, okay, if they are in a pure state. And the intermolecular hydrogen bonding between the carboxyl groups prevent the formation of the anhydride at lower temperature. But once they are either in amorphous state or when they are applied to cotton, the temperature for the form the anhydride is just reduced, maybe by 30, 40, 50 degrees centigrade. And this is my work. And also I studied catalysis. I don't have time to discuss, which is so the sodium hypophosphite, which weaken the hydrogen bonding of carboxyl group in polycarbic acid molecule are cutting. So weaken the hydrogen bonding, and it accelerates the formation of 5-membered anhydride intermediate. But this is, we have pretty very convincing evidence. Then the third conclusion is that it also accelerates esterification between the anhydride and the cotton, which is we have evidence to prove, but we still could not propose a detailed mechanism. And this is about the catalysis mechanism, my work published. And the last one is 2001. And then, of course, as a textile chemist, I not only want to understand the reaction, but I want to understand, I want to develop more effective, more practical DP finish agent. So, we have BTC, but this is in the 1988 paper by Dr. Welch. But BTC was not commercialized only to maybe 10 years ago in the Chinese company, but still more expensive. Then the Beth Andrews, who the time was in the USDA, who was also received the honor medal in 1990s. And she published a paper in 1991 using citric acid. But the citric acid is far less effective. So my work is all based on malic acid, which is most abundant, it's cheap, and but it is bifunctional. So this is my work, how to make it be able to cross-link, can have reactivity or effectiveness comparable to that of BTC, to that of DMDHU. That was my purpose. And first system is citric acid and with the polymeric acid, which is a commercial product. And we find the citric acid has a low reactivity because of the OH group, because the citric acid has a hydroxyl group. And at the same time, I also find polymeric acid form 5-member anhydride intermediate at a relatively very low temperature. But because it has a low reactivity, because the esterification is a reaction in the solid state, because after cure, it is not in the solution. And simply just the molecular weight is too big for the reaction to take place. So it can estify, can actually form cross-linking, but at a much lower level. But we also find the polymeric acid anhydride react with citric acid, the OH group of citric acid. So this is a new finding. And so what happened is, if we use this on the fabric simultaneously, in the one finished solution, and it form that esterification, then if it eliminate this group, the OH group, it make citric acid effective. Citric acid also less effective because it only have 3 COH. But by doing this, you may increase the functionality, the number of functioning group for a cross linkage. So this is also making it effective. And here, I just show you the proof. Proof we use the TPMA is one of, we call it TPMA, so we use 2 polymeric acids, one of them. And we use a mixture. They have a total OH group with this titrated. It is around, practically it's identical. But the ratio is different. This is more ratio. Then you will see the Greenville recovery angle. Okay. Total citric acid 100% is 236 degrees. Then for the total 100% pure malic acid is 130 degrees. For citric acid, 204 degrees. But at the 15 to 85 is 264 degrees. Higher than both. Now this is indicated synergistic. Somehow in this ratio, it becomes more effective. But in order to further confirm by to the two wash is even more clear, because it's here you have the 230 degrees for polymeric acid, you have 231 degrees for citric acid, but with the 15 to 85 ratio is 252 degrees. So it's a 200 degree significant. That's significant. After team wash, it could eliminate all other possible factors contributed to the linear recovery angle. And here, just show you that this is in the finish. We have the 2 formulas at different pH, the DMDHU, and we use relatively high the current temperature, which is the drawback. And then so the lingo recovery angle is much higher than DMDHU. And the DP rating is higher. But at the same time, the strength retention still is higher, particularly 2.7 of 62% retention. And in the warp, in the 4.6 retention in the feeding, but the DMDH is 53, 43, so it's a slightly higher, bigger retention strength than the DMDH. Okay, here this is the first one, and we actually achieved some commercial success, but it was not continued, and we have a patent. This is because FMC funded this research. So. Then the second one is we use I need to be fair. Use polymerize. Okay, polymerize use aqueous solution, and this is it's a mass spec. So this is 433. This is twice as high as BTCA. And this is the mass spec explanation. We have mostly for degree population 3 or 4. And then this is polymerization reaction. And we will find it actually has a similar recovery angle, similar DP rating as DMDHU, but the strength retention we have higher. Strength retention we have 54% versus 46%. And so this is another durable, it's high performance durable press feeding system, and it is relatively very low cost and also has a high solubility. BTCA has very limited solubility. This is commercialized in China. And this is the paper for me. And then we have another one is malic acid. We just use malic acid. This is the most recent one. The malic acid, we see there is 2 reactions when we use malic acid on cotton. One is the acidification. You will see this ester. Second one is it has the addition of the malic acid to the double bond of malic acid added by the pH group in the high phosphate. And here you see the lingo recovery angle and also the phosphate concentration, it is almost the same. And here, so this is what happened is malic acid first will form acidification, but this bond is reactive with the hard phosphide. So hard phosphide actually become plus linker between the 2 malic acid acidified to the cotton. So this is we'll see it has, because the DMDH has a similar DP rating and also linker recovery angle, but it has relatively higher breaking strength retention. Also carrying strength also modestly higher. Okay. And so 2 minutes. Okay. And this is I will show you the flammability. Okay. This is we call it heat release rate. This is a major parameter for the flammability. And it is, even though it is not flammability, but the heat release. And then we use malic acid and the hard phosphide. Actually, we increase the temperature, then we will see the peak heat release rate is decreased. This is because of the further decrease is because of the addition of phosphorus. So we can add another 1% of phosphorus to the content by the malic acid and the hard phosphide. And so this is increase the child yield. And so my time up. The second is about the strength retention. I think I don't have time, so I just this is under the AATCC paper. So we also have a much longer version on the website. so I don't have the time to I just, this is, we use the polyvinyl alcohol to react with the surface clothing agent, so preserve the softness of surface to improve flux abrasion resistance. So this work. Okay, we form the polymer film in the scanner electron micrograph. Okay, so this is all my work, and I acknowledge that the DOE and the Department of Commerce, AATCC Georgia Traditional Industrial Program, and the company include P&G, Dow Chemical, ExxonMobil, has incorporated FMC Union Carbide, and the Chinese company, Diamond Chemical, to support all these years. Thank you.